sigma on 1 is increasing. Epsilon Q2 is 0, and epsilon Q3 is 0. Now condition 1, or condition 3, will actually show you something, or will tell you something about the von Mises plasticity. What it will tell you is the von Mises plasticity does not predict any failure when sigma on 1 is equal to sigma to 2 is equal to sigma 3, 3. When sigma on 1, sigma to 2, and sigma 3, 3 are very close to each other, the von Mises plasticity predicts that the material will not fail. And it happens that in this particular situation, if you're able to confine a specimen, then you're able to increase sigma on 1 in tension or in compression by large amounts without the model predicting that failure will occur. And whether you're able to apply this particular condition in reality or not, you can actually pull and see, that's a different issue. In practice, whether I'm able to apply this condition or not, that's a different issue. Usually, you're not able to apply such a condition where you're confining both directions, especially in tension. In compression, maybe, but in tension, it might not be possible, practically. But nevertheless, let's see what the model predicts. In the elastic, now, we know that there's an initial elastic stage. How do we know that there's an initial elastic stage? Only because the relationship between the stress and the strain follow this curve, which tells me that initially the initial yield is not 0. The initial yield, I don't develop plastic strain until the von Mises reaches 400. If you're using a Ramberg-Osgood approximation, you're developing plastic strain from the beginning. So we have sigma on 1, epsilon 2 elastic is equal to 0, is equal to epsilon 3 elastic. Epsilon 2 is elastic is equal to sigma 2 over E minus Poisson's ratio sigma 3 over E minus Poisson's ratio sigma 1 over E. And sigma 3 over E minus Poisson's ratio sigma 1 over E minus Poisson's ratio sigma 2 over E equal to 0. From these two equations, you will get that sigma 2 is equal to sigma 3 is equal to Poisson's ratio sigma 1 divided by 1 minus Poisson's ratio. Sigma 1, or sigma von Mises, is equal to the square root of sigma 1 minus sigma 2 squared plus square root over 2 and this, at the onset of yield, this will be equal to 400. So when you substitute, you'll find that sigma 1 will be equal to 1 minus Poisson's ratio divided by 1 minus 2 Poisson's ratio multiplied by 400, which is equal to 700 MPa. And in this case, sigma 2 is equal to sigma 3 is equal to 300 MPa. So So we have to increase the stress up to 700 to reach yield. Again, whether this is just to show you that because of that confinement, I do not predict any flow of the material, and because I can't predict any flow using this material model, I'm predicting really high stresses before the material actually yields. In fact, this material model, if you say sigma 1 is equal to sigma 2 is equal to sigma 3, and you pull forever, this material model will predict no plastic strains, no failure. But again, in practice, this does not often, we don't have this issue. In practice, this material model works really well, because usually there is an area where you can't have this confinement of stresses. Usually in any component, you don't have a confined state of stress. So beyond 700, beyond this, we are going to follow exactly what we did. Now we have sigma 1 is increasing. I control this. Sigma 2 and sigma 3 are increasing. I don't have control over them because they come from the restraints. Epsilon, of course, prime. The epsilon plastic also increases. So I'm looking for equations for all these changes. These are obtained from the restraints and the consistency condition. If I don't have a restraint, I will probably give you another condition by which you know how sigma 2 and sigma 3 increase. For example, say the 3 increase linearly together, or sigma 2 is constant at a particular value. Sigma 3 is constant at a particular value. So for this condition, we have the consistency condition phi dot 0, so partial sigma 1 is like partial sigma 1, sigma dot plus this is the first equation. Again, I'm controlling this, so I can calculate at least one, but I cannot calculate the other two. I cannot calculate the other two, I need two more equations. The two more equations are epsilon 2 equals 0. This is equal to sigma 2 dot over E minus Poisson's ratio sigma 1 dot over E minus Poisson's ratio sigma 3 dot over E plus, so this is the elastic component. Plastic strain component is equal to this multiplied by partial phi by partial sigma 2. Epsilon dot 3 is 0. These are three equations. If I control sigma prime, sigma dot 1, then this is three equations in 300s. And you can use the numerical differential equation solver to find the functions, or you can just incrementally do it by hand, by just assuming deltas and integrate numerically. when you look at the curves, S22, sigma 22 versus sigma on 1 up to 700, and then we'll have a different slope. That's from plastic on 1 versus sigma on 1 up to 750, up to 700, and then we'll have slope. But you'll find that even at 1050, the plastic strain component is very small, because I'm not allowing the material to flow. Plastic strain component. That's from plastic 2 is increased and negative, but the values are very small. Negative 0.007. It's very small plastic strains develop, even though the stresses reaches up to 1050. They're equal, and they're equal to the negative of the elastic strains. So in the next lecture, we are going to cover the remaining part, which is what happens if the yield stress changes in the different directions. If sigma on 1, as I increase the yield, so how to include the Bollinger effect in all this? If sigma on 1 increases in one direction, how can I predict that sigma 2 is going to increase? Now, for your assignment, here are, I just want to give you some hints so that you understand what you're doing for the assignment. Yes?
The program that you told me, the mathematical code regarding this case, you increase it by 13 times.
Yes.
Can you please explain how you should do that?
You don't have to introduce the parameter of time. All the questions that are in the assignment, you don't need mathematical for. You have to do by hand. It's easier to do by hand. There's no numerical integration. Okay? So for the assignment, do it by hand, not by mathematics. Okay? It's easier by hand. Now, how I did that was, well, I have to remember actually. Weird.
One was considered to be equal to t.
So I made everything function of t, yes.
Yeah, sigma 1 is increasing.
Yes. So basically, I solved the differential equations. I solved the differential equations that say the following. Sigma, so I have the functions of sigma 2 of t, sigma 3 of t, and sigma 1 dot of t. So I have the 4 equations, or the 3 equations, and I added an extra equation. Sigma 1 dot of t is equal to 1. I just added this extra differential equation. So when you look at these, I've got 1, 2, 3. I added sigma dot 1 is And I gave the initial condition sigma 1 of 0 is equal to 400 or 700, and sigma 1 of the time equal to 1 is equal to whatever number you want. Okay? So I just added an extra equation for sigma 1 and the function of time.
So for the previous assignment, we only have one equation. That's really slow. But we are increasing all the stresses together.
Yes.
Here we have three equations.
Yes. Because I don't know how this is changing. In the previous assignment,
We know
you
all.
knew how these are changing. Yes? Any other question here?
So the assignment we have to define is equal to 1 is equal to 1 is
I can't hear you, sorry.
for the assignment. We
Which
have
one?
to
The previous
for
one?
The assignment, yeah, previous assignment. We have to define that sigma 1 is equal to 1 and again is equal to 2 is equal to 1 and sigma 3 is equal to 1 because we consider t.
You're talking about the previous assignment?
Previous assignment.
No, the previous assignment, you have the ratios. In the previous assignment, you had the stress was equal to, let's say, 100, 100, 100, 200, 300. That's at the final stage. All these are increasing together. So all these are a function of t. So sigma 1 is equal to 100t. Sigma 2 is equal to 200t. Sigma 3 is equal to 300t. So all these are function of t, but the only one variable is t. I don't need any additional equation. Is that? And so that's why I don't need these additional equations. I only use the first one because I know how all these change.
So you don't know H.
Yeah, I know H. That's what
actually
actually.
really stuck on how to find it.
H is a function about it's a function of
It's the slope.
equivalent plastic string.
This is H.
Yeah, it's a function, right?
It's a function, depending on how you present this relationship.
Yeah.
If this relationship is linear, H is constant. If what is H?
We should consider H constant at each step or not?
Yes, you can.
Since we are income.
Yes. So it depends. Yes, that's exactly what I'm going to say. If this is the relationship between yield and epsilon B, H equal constant. If I have an analytic equation, let's say sigma yield example equal to A epsilon P power M, then H is equal to MA epsilon P power M minus 1, for example, or whatever. Okay? If sigma yield versus epsilon P, if I just give you this, then H will vary according to where we are. Here, it will be this slope. This will be smaller slope. Here will be a smaller slope. It will be even smaller slope. Just a slope.
The assignment, I just took it as the whole, whatever. I just went straight from like grade to EP, I guess, at the end.
So you took this as a slope?
Yeah.
It's just an approximation. I mean, you basically assume that the relationship between sigma yield and epsilon P,
Yeah.
you ignored all these. You assumed this relationship.
Yeah.
That's what you did. And, I mean,
It's acceptable.
well, you just have to be aware of what you did.
Yeah.
So, whether it's acceptable or not, what's acceptable is that you realize that you ignored this fact. And so, let's say that's your plan. You're doing something by hand. You have to say, I assume that the relationship follows this. But if you assume that the relationship follows this, and then you use this H, then that's not acceptable. Yeah?
So in each increment, all the stresses are increasing, and then
What are you talking about? The same problem?
yeah,
Yeah.
at the final stage of each increment, we have the stresses. We need to calculate the von Mises and go, or the von Mises equal to sigma y, and then again we go to this curve and
Yes. So basically,
compute this slope again at the end of the step.
yes. So that's what we're doing. We're just traversing the curve. Yeah? So you just use one H, basically. Basically, just like red. And that's fine. But at least you know. I mean, it's one small problem in one small assignment. So it's not that hard. Any other questions before we look at the assignment? So for the assignment, the first question we talked about earlier. The second question we have, assuming that in a uniaxial state of stress, the elastic plus the plastic strain is equal to sigma over E plus sigma over m plus 1 over E over another material constant. This is a material constant. These are two material constants. This is the Young's modulus. This is the elastic strain. This is the plastic strain. And I'm asking you to show that d tau by d gamma 1, 2 is equal to 1 over g plus 3m plus 1 root 3 tau power. So what is it that I'm asking? Well, basically I'm asking for the relationship between epsilon dot E 1, 2 plus epsilon dot elastic 1, 2. What is here? Multiplied by sigma dot 1, 2. This is what I'm asking for. Because this is equal to gamma dot 1, 2.
What is tau? Is it shears?
Yes, that's sigma 1, 2 is equal to tau. This is what I'm asking for. And d tau, or d sigma 1, 2 by d gamma 2 is equal to sigma dot 1, 2 divided by gamma dot 1, 2. Which is equal to 1 over whatever that is. So you're just going to have to follow exactly what we did here, but just explicitly, not numerical. So you're going to get those equations, and actually, yeah, just find those equations and it's just going to come out right away. That's just, what is this? What's the plastic strain? Oh, I'm sorry. There's no bar here. There's no bar. This is basically using the flow rule. Dot, partial phi, and partial sigma 1, 2. Whenever I see partial phi like partial sigma 2, it's 3 over 2 S12 divided by sigma 1 means. Now what's sigma 1 means when I only have sigma 1 2? And what's S12 when I only have sigma 1 2? In the other question, now don't forget to look at the other questions in the handout because the other questions are what appeared in previous final exams. Okay. So the last question. We have a relationship between this. So this is an explicit relationship. Absolute P dot is equal to A3 sigma yield squared sigma yield dot. And so H is equal to D sigma yield by D epsilon P is equal to sigma yield dot over this is equal to 1 over 3A sigma yield squared, which is 1 over 3A. Instead of sigma yield, I'm going to use sigma von Mises because they are equal as long as I'm developing plastic strain. The yield and the von Mises are the same. When I have a pipe, with an internal pressure P1 and an external pressure P2. And we want to know absolute plastic 1,1 and absolute plastic 2,2 as for different values of P1 and P2. Knowing that in each case, sigma 1 is equal to, this is the stress in this direction, sigma 1 in this direction is equal to force divided by the area sigma 2,2 in this direction, in the circumferential direction, is equal to P1 minus P2, the diameter divided by 2t. Now in the first, let's just look at in the first condition. P1 goes from 0 to P, and P2 goes from 0 to 1.5 P. And I want to show that the plastic strain 1,1 is equal to 9A some function f over 2, where f is the value that f is equal to, I'll show you right now, where f is equal to the diameter multiplied by the pressure divided by 4t all cubed. So how do you do this? Well, simply you have the consistency condition. The consistency condition starts from the beginning because we're developing plastic strains from the beginning. Phi dot equals 0. Partial phi. So find S11 and S22. 3 over 2 S11 divided by sigma 1 Mises, sigma 1 dot, plus 3 over 2 S22 over sigma 1 Mises, sigma dot 22 minus H epsilon dot P equals 0. I don't need another equation because I know how sigma 1 and sigma 22 change, because sigma 1 is equal to P, sigma 1 dot is equal to P dot, and sigma 22 is equal to 1.5 P, sigma 22 dot is equal to 1.5 P dot. So everything is function of P dot, and you can integrate with respect to P dot, where P dot changes from 0 to 1.5. Sorry, from 0 to P. So everything here, you're going to get the relationship between epsilon dot equal function of P dot. So epsilon P from 0 to P d function. And epsilon 1 P dot is equal to epsilon P. Again, function of P d, function of P P dot. So epsilon dot P, so epsilon P 1 will be the integral of 0 to P, this function of P d. And it will just come, all these numbers will come out once you do it that way. Okay, so for your for the assignment before the plasticity, I promised you I will give you a handout about the models for the strain energy density function, and I will probably cover this after plasticity because I don't want to confuse you right now. But take a look at this handout, and I'm going to post it as well. I forgot to post it. But this handout will make functions, so let's just talk about it for a sec. Actually, I can cover it right now. So I'll give you 5 minutes just because it's a totally different topic, so not too confusing. So 5 minutes and we'll talk about it.